Kia ora. Follow along as I talk about transformers and specifically some of the things you'll need to know for the theory exam for New Zealand. This is a basic 230 to 12 volt transformer. I'll be talking about some of the different ways they're wired and some of the different principles. Now, I'm only going to touch base a little bit on a single phase transformer. Most of the rest of the time I'm going to talk about three-phase transformers. So just as a basic, a transformer has two windings, the primary and the secondary. The primary comes down and let's say that's 230 volts. And then it has a laminated iron core, and then it has its secondary on the other side of the iron core. And in this case, it's a 12 volt. The way that a transformer works is current is passed through the primary winding and creates a magnetic field that then induces onto the secondary winding of the transformer, and because of the amount of turns that this coil has compared to this coil makes the difference in the voltage. One of the main differences between a single phase transformer and a three-phase transformer is just that there is three phases being transformed, not only one. So there's a number of different connections for a three-phase transformer. So there are two different things to remember. Star connection and delta connection. A star connection looks like this. The coils are here, here, and here, and you'd have phase 1, phase 2, and phase 3. And as you know, because of AC theory, that the connection point in the middle here works because of the difference in the sine wave. The other connection is delta, and that is like this. A triangle with three coils all connected one after the other, and you'd have P1 and then P2, P2, P3, P3, and then the other end of P1, or any orientation but between each coil as a phase. Now, the different ways you can connect them are star-star. This is on the transformers, so this star will induce directly onto this star. You can have them delta-delta. Same again, from the one delta to the other. You can go delta-star, and you can go star-delta. Now these two here in New Zealand are the most common for three-phase transformers, but you do have these as well in other applications. Transferring this into wiring diagram, the primary is delta, so you have your three coils. I'm just going to do a scribble for the coils for ease of time, and you've got your three coils here and your laminations between. If this is star, you have it comes down to its star point. Then you call this part here the center. It can go all the way along, and one leg from each one needs to connect to it, because see, one leg from each coil would connect to this central point, and then these other ones come off and are the outsides. So you'd have, let's call it A, B, and C. Then on the other side, the delta side, all ends connected. So what we need to do is just go from one to the other, one to the other, and then back together again, like so. And then you just need to connect your three phases to the end points of the coils. So we can 1, 2, and 3. And that's A, B, and C, like that. So this is a delta, and that's a star. And then obviously if you have it the other way around, then you just make this the primary and this the secondary. So that's the basics of the wiring of a three-phase transformer. Now I'm going to talk a little bit about transformer losses. So there's two main ways that transformers have loss in power: copper loss and iron loss. Copper loss is caused because of the resistance in the coils or the windings. Because of Ohm's law with voltage, current and resistance, if the resistance is higher, the current will lower because the voltage is staying the same. They call it copper losses simply because the windings are generally made out of copper. Now, there are two types of iron losses. I'll write them down for you shortly. Both of them are a direct effect from magnetism from the electromagnetic fields. One of the ways they reduce the magnetism on the iron core is by laminating it with small sheets of iron which has varnish in between. You've got the eddy and the hysteresis. So if you want to know some more about that, search them up and have a look. Okay, we're going to work through a three-phase transformer and some of the calculations. So bear with me as I write them down and walk you through them. So you've got line voltage and phase voltage. The line voltage is between the two phases and the phase voltage is of one phase. You also have that on the secondary winding. When you have a delta star connection, the phase voltage is whatever the ratio of the windings are. So if it's a 2-to-1, then the phase voltage on the secondary side will be 200 volts if the primary is 100 volts. Now I'll show you the other calculations to find the other values we're after. Now I'm going to use a slightly different scenario because I've got one here that I can work out of my apprentice workbooks. Let's say that this here is now, I will do this in blue, this is 11 kV between here on the line voltage. It's a 50-to-1 ratio. The output is 250 kVA. Okay, so that's all the information we know, and I'm going to work you through getting the primary line current, the secondary line voltage, the secondary phase voltage, and the secondary line current. Okay, to get the primary line current, S is equal to the kVA of the transformer being used. 3 times phase voltage times phase current. And to rearrange that, because we're after the primary line current, which is this one here, we go primary line current becomes S divided by 3 times primary voltage phase. Okay, and to put that how we need to, that is going to equal the S is the kVA output. We'll talk about more about the S soon. So that is 250,000 divided by 3 times and the primary current, primary voltage, which is 11 kV, which is 11,000. Because I'm only touching on some parts of three-phase transformers and not going through the whole theory of it, for the people that are unaware, on a delta connection, the line voltage and the phase voltage are the same. Do that calculation and you'll find that it equals 7.575. That is the primary phase current. We're after the primary line current. And to get a primary line current, you need to go primary line current equals the primary phase current times the square root of 3, which is 7 0.575 times the square root of 3, which equals 13.12 amps. So that's our primary line current. So that's how you receive the primary line current. So the secondary line voltage calculation is that. So primary line voltage times 1 divided by 50, which means 11,000 times 1 divided by 50 equals 220 volts. So our secondary line voltage is 220 volts. Now we can find our phase voltage. So our secondary phase voltage is the line voltage divided by the square root of 3, which is 220 volts, because we just worked that out, by the square root of 3, which equals 127.01 volts. So there we go, we now have our secondary line voltage and phase voltage, so that's 127.01. In a delta star transformer, you would always expect that the line voltage will be larger than the phase voltage. Our last calculation we can do is work out the secondary line current. The secondary phase current equals S over 3 times the secondary phase voltage, because we are on the secondary side, so that's the secondary, which is 250,000, because that's the kVA of the transformer, divided by 3 times 127.1, which equals 656.1 amps is our line current on the secondary. So just like in a delta wiring, how the phase voltage and line voltage are the same, when you have a star, the line current and the phase current are equal. So that's quite a lot of calculation for you. Take a snapshot, try swapping this out with some other ones, see how it works. Even if you know the full numbers of a transformer, plot them into these and give them a go, and then you know that your answer should be 346 if you use my first example. So then you can try the calculation out and know that you got the right number. So this video is going to be on the longer side, but there's two other things I want to touch on. The first one being three-phase tapped transformers, or just a tapped transformer. The way that works is on this side you will have a winding, however long it is, and on the other side you have another winding, but it has multiple points at which the other line comes off. So if we call this the end, it comes up, and then the coil is here, but there's a join on point there, a join on point there, and a join on point there. There's multiple reasons for this. It gives the power companies a way to be able to change the voltage if they need to, so they could have this at 250 volts, or 240 volts, or 230 volts, or 220 volts, and depending on the demand and how much current is getting drawn, they could up or down their voltage to match, so that they can supply the right amount of power for any dwelling. That's about all I'm going to touch on the tappings. The next thing I want to talk about is the true power, the reactive power, and the apparent power in the power triangle for a three-phase transformer. Okay, so there's a couple of calculations and things to know about the power triangle. Now I'm just going to read this out because it explains it the best. The true power is the resistive power consumed by a balanced three-phase load. It is called true power and active power, and it is measured in watts, kilowatts, or megawatts. The formula to find true power is P for power by the square root of 3 times the line voltage times the line current times cos tangent, and that is the power factor. Okay, that's true power. The next we have reactive power, which is the product of voltage and current and is called kilovolt amps reactive. So Q is the letter we give it, and it is measured in volt amps reactive. The calculation to find out what the reactive power is 3 times the phase voltage times the line times the phase current sin tangent. So the last one we have is apparent power, and it is the product of voltage and current, and it is measured in volt amps, kVA, like our transformer over here. The formula to find S is 3 times the phase voltage times the phase current. Okay, so then you end up with this triangle, and you have here you have Q, which remember is the reactive power. On the top you have the apparent power, and on the bottom you have the true power. And this degree in here is, ta-da, the power factor. So as the last little thing for this video, I thought I'd draw a little diagram as to how the power factor can affect how well a transformer works. If you look at this first triangle here, it's a 100 kVA transformer with a power factor of 0.95. That means the true power is going to be 95 kilowatts with a kVAR of 31. So that's producing pretty well. It's near to its apparent power. Whereas if you dropped the power factor down to 0.7, it now can only produce 70 kilowatts of true power, and its kVAR goes up to 70. So the closer you have your power factor to 1, the better off your equipment and three-phase equipment is going to work. There's still heaps more to learn about transformers, but that's all for now, and I hope you have found that helpful. And as always, follow for more from an NZ tradie.